Applying Newton's second law to the inclined plane, we know we have the force normal and our weight, the force of gravity. Newton's second law says that the net force is directly proportional to the mass and directly proportional to the acceleration. The net force is also defined as the sum of the forces. So the net force is the sum of the forces, and that force is ma. If we look at each dimension separately, the x dimension and the z dimension, let's first look at the z. We have our coordinate axes like this. So here's our x, here's our z. As we look at an object on the xz plane, this object that's placed right here at the red dot in the free body diagram is not accelerating in this direction. There is no acceleration in the z direction. If there were to be acceleration, that means it would be taking off like a rocket in this direction, or it would be breaking through the surface and falling through. So as long as it's on the surface, there is no acceleration vertically in this direction. Any acceleration might occur in this direction, but that is independent of the vertical direction. So if we look at the z direction, the acceleration in the z then is going to be due to the force normal minus the force of gravity perpendicular. And if that acceleration is 0, that means that that term is 0. And that means that the force normal is minus Fg1 equals 0. And just rearranging this, what we find is that the force normal is equal in magnitude to the force of gravity perpendicular. In other words, these two must be equal in size. If the object on the inclined plane is not accelerating in this direction, then Fn will always be equal and opposite to Fg perpendicular. That also means then that Fg must always be larger than Fg perpendicular. So when in drawing these forces, however large we draw Fn, Fg perpendicular should be equal in magnitude, equal in the other direction. And so this is how we apply Newton's second law, N2, to the forces on the inclined plane.